Welcome to this National Weather Service training presentation, What is a POP and how do I use it? Offered by the National Weather Service office in Jackson, Mississippi. First off, the acronym POP, P-O-P, refers to the probability of precipitation. Officially, the POP for a specific location refers to the probability of 1/100th of an inch or more of precipitation at a specific location over a given time period. For the purposes of an official National Weather Service forecast, the given time period is usually 12 hours. For the National Weather Service, each day is divided into two such periods, day and night, which begin at 6 a.m. or 6 p.m. local standard time. A short mathematical POP definition is that the POP equals an expression of confidence multiplied by an expression of area where that confidence is applied, where the confidence is a confidence expressed as a percent of precipitation of at least 1/100th of an inch occurring, and the area is a percent of area expected to be covered by this precipitation. Usually, the National Weather Service forecaster is most concerned with the confidence factor. This is largely because the modern detailed National Weather Service graphical forecast, on which text-based forecasts are derived, usually deals with many small areas where precipitation coverage can be assumed to be all 100% or nothing, 0%. As a result of this, it is obvious that high forecaster confidence usually results in a much more definitive POP forecast. An exception to the previous is often during the summer, when typical, somewhat random afternoon thunderstorms require the forecaster to make estimates on expected rain coverage over larger areas, making the area portion of the previous forecast equation more significant. In this example, the aerial coverage of showers and thunderstorms in the southeast quarter of the forecast area is around 20%. So how do we forecast POPs? Forecasters use experience and expertise to adjust computer-derived POPs up or down. Often, weather situations will arise where forecasters have very high confidence of rain and will raise these computer-derived POPs significantly, such as in this situation where a solid squall line of thunderstorms is expected to push through the forecast area ahead of a cold front in the next 12 hours. This squall line is expected to remain more or less solid, which argues for pushing the POP at or close to 100% for the forecast area. But just as often, an expected weather situation is judged by the forecaster to argue for no rain much more strongly than the computer model suggests. As previously stated, as a starting point for the forecast, we generally use output from computer models. These starting points are deeply rooted in statistics and historical weather information, matching cases when past weather conditions were similar, and then considering what percentage of those cases resulted in rain. Below is a simplistic example of how this process works. The chart on the bottom left shows simulated atmospheric forecast conditions for Jackson, Mississippi for the next day. The next two charts show past situations where atmospheric conditions were similar to what is being forecast. Since rain resulted with both of these past conditions, it argues for a high POP in this forecast case. Often we receive questions similar to, I need to know if it is going to rain or if it is going to be dry Saturday at 123 Main Street, or this is just a representation of a specific location. Taken at face value, this question is specifically asking what is the 12-hour POP for the daytime Saturday at this specific point, 0% or 100%. Often this sort of question cannot be answered with absolute certainty, and almost always never more than a day or two in advance. This is the case because 0% pops, or especially 100% pops, are not often used beyond the short-term forecast, and even in the short-term forecast are still not used a great deal. Put simply, if we say for a given point and for a given 12-hour period the chance of rain is 100%, then we are essentially saying measurable rain is a certainty. If we say for a given point and for a given 12-hour period the chance of rain is 0%, we are essentially saying that there is no way measurable rain will occur. Our credibility would be negatively affected if these forecasts of highest confidence do not verify. Think of the cry wolf syndrome. So in order to express a rainfall forecast most scientifically, we would rather express our certainty concerning rain or no rain in terms of probability, or a pop number. But some people not used to dealing at all with statistics find it difficult to find value in probabilistic output, especially if the pop is closer to 50% than 100% or 0%. One way to use probabilistic rainfall forecast is to make planning decisions using a cost-to-loss ratio. The cost-to-loss ratio, CLR, mathematically equals the cost of planning for adverse weather divided by the potential loss suffered if adverse weather occurs and it is not planned for. Important things to keep in note with the cost-loss ratio is that the cost does not necessarily have to be monetary, but making weather planning decisions based on the cost-loss ratio philosophy is meant to maximize efficiency in the long run. We will go into more in-depth about the cost-loss ratio, and how it works, and how you can apply the principles to your advantage at the end of the forecast in the appendix. So now we'll talk about some misconceptions associated with the probability of precipitation forecast. A high pop value, such as greater than 70%, means that a significant amount of rain is anticipated and/or the time period in question will be a washout. This is not valid. Another one, a high pop forecast for today is wrong when it only rains a little for 5 minutes in the morning while the rest of the day is dry and mostly sunny. This is wrong. In fact, the pop definition says nothing about how long it will rain in a given 12-hour period or the amount of rain expected, other than at least 1/100 of an inch is anticipated. These are the most misunderstood aspects of the pop forecast. Some more misconceptions. In the summer, a low pop value, such as less than 30%, means that it will not rain, or if it does rain, it will be rather insignificant. This is not valid. Often, the aerial coverage of afternoon thunderstorms is rather low and results in a low pop forecast for most locations. However, an isolated afternoon thunderstorm can sometimes be slow-moving and vigorous, and therefore produce 1 to 2 inches of rain over the affected location. This is the case in this graphical example shown here, where heavy rain at the location just southeast of Meridian is illustrating this principle well, where the coverage of precipitation is low, but that heavy, slow-moving thunderstorm is likely going to give somebody a great deal of rain. So this slide is going to endeavor to drive home the point of the pop statistics and how they work. If a pop is high, but less than 100%, forecasters expect that on some occasions it will not actually rain. In an example of this, the forecast for a particular 12-hour period at one spot is 70%. This forecast is basically saying that for 10 similar forecasts where everything is the same or close to the same, the forecaster expects it to rain 7 times but remain dry 3 times. Conversely, if a pop is low but more than 0%, forecasters expect that on some occasions it will indeed rain. As an example, the forecast for a particular 12-hour period at one spot is 20%. The forecaster is basically saying that for 10 similar forecasts, the forecaster expects it to remain dry 8 times, but rain 2 times. The analogy of loaded dice works out well when forecasters are trying to express the probability of precipitation. So much like a 50% pop is similar to flipping a quarter where heads is dry and tails is low, a 20% pop would be rolling a set of dice that is loaded towards giving a dry output, while a 70% pop is similar to rolling a dice that are loaded towards giving a wet output. So let's say you need more information than what the pop gives. Remember from the previous slides that the official NWS pop forecast for your location is not going to tell you how much rain might fall and exactly when it might fall within a given 12-hour period. To get this more detailed weather information, the best place to go is our webpage, the National Weather Service Jackson's webpage at www.srh.noaa.gov/JAN. Now, to navigate this home page that the address will take you to, the best thing to do is use the point-and-click forecast, where you click on a specific point that you're wanting to know the forecast at the map, and that will take you to a text forecast for that location. And within that page will be an hourly weather graph that you can click on and enlarge, which will show you timing for when exactly is the absolute best chance of precipitation within a 12-hour period and how much rain is expected to fall. Now, where else can you get more detailed information such as this? These sources may not be quite as good or thorough as our main webpage, but there's another National Weather Service website focused on the lower Mississippi Valley that displays graphically many of the forecast parameters in detail, such as weather and rainfall amounts. That address is given in number 1. Also, if you have a NOAA weather radio or a NOAA all hazards radio, it can give specific radio broadcasts to give you rather detailed weather information, as long as it is tuned to the proper frequency for your location. Of course, it can also give you life-saving information on weather alerts. Thank you for viewing the National Weather Service Jackson's probability of precipitation training. Remember, after this slide, there will be some detailed information concerning the operational utility of the cost-loss ratio. Otherwise, we hope our efforts have improved understanding of POPs and will allow you to maximize usefulness of the official National Weather Service precipitation forecast. Please feel free to communicate positive or negative feedback about this training to the email address listed below or the contact number. So now on to the appendix, where I will attempt a more detailed explanation of the utility of the cost-to-loss ratio. Remember from the previous slide that a good way to use the probabilistic rainfall forecast to make planning decisions is to implement the cost-to-loss ratio, which mathematically equals the cost of planning for adverse weather divided by the potential loss suffered if adverse weather occurs and is not planned for. Remember that the cost does not necessarily have to be monetary. So, if the POP is greater than the cost-to-loss ratio times 100, then the cost-loss ratio principles tell you that planning should be made to account for potential bad weather. Conversely, if the POP is less than the cost-to-loss ratio times 100, then planning does not need to be made to account for potential bad weather. I must emphasize these words of caution that making weather planning decisions based on the cost-to-loss ratio philosophy is meant to maximize efficiency in the long run. Meaning, using this philosophy on a one-time basis may not be the proper strategy and may not result in the result that you would want to see. It just meant that over the long run, if you use these philosophies to make decisions, it will maximize your time expenditures or your monetary expenditures. It's also worthy of note that using this philosophy is not recommended if failure to plan for potential bad weather could lead to catastrophic consequences. So let's go over an example. So let's say we need to cut hay and want to do so now, so it would be possible to get a decent second cutting of a max value of $1,200 before the season is over. But if we cut now, there is a decent chance of rain on Sunday where the POP equals 60% when the hay is drying underground, which will lower its value if it gets wet down to $500 from $2,000. So do we cut now to allow for a second cutting to be possible and take chances with rain and potential loss, or does it make more sense to wait for better weather? So we're going to define the variables where the cost of planning for adverse weather is $1,200. This is what happens if you wait to cut hay and then definitely don't get a second cutting. We cost ourselves $1,200. The loss if adverse weather occurs and is not planned for is $1,500. This is what happens if we cut now and it does rain on the hay and degrade it. So the POP equals 60%, and this is the chance of the hay getting wet underground. This is defining all our variables. So remember from the previous equation that the cost-to-loss ratio equals the cost of planning for adverse weather divided by the potential loss suffered if adverse weather occurs and it is not planned for. In our case, the cost-to-loss ratio equals 1,200 divided by 1,500, which equals 0.8. So we'll do the final figuring to see if weather planning should be taken. If the POP is greater than the CLR times 100, planning should be made to account for potential bad weather. If POP is less than CLR times 100, planning does not need to be made for account for potential bad weather. So in our case, 60 from the POP is less than 80. So the cost-loss ratio philosophy tells us that planning does not need to be made, so ignore potential bad weather according to the cost-loss ratio philosophy. So let's go through another example to help illustrate the principle. In this example, we need to apply sealant to the driveway, which takes an estimated time of 5.5 hours. We need to do this before next weekend, and we would like to do it Saturday when I have plenty of time to do it. The problem is there is a low chance of rain Saturday night. The POP equals 25% before the sealant dries. If it does rain, then I will have to do it again Sunday when other obligations will make the process longer. The estimated time equals 7 hours. Should I apply on Saturday and take my chances with rain, or wait until Sunday, which I would rather not do since I have other plans? Let's define the variables. The cost of planning for adverse weather equals 1.5 hours. This is the greater amount of time I will spend on the chore if I do it Sunday instead of Saturday. The loss if adverse weather occurs and is not planned for is 7 hours. This is a loss of time if I do the chore on Saturday and it rains Saturday night and I have to do the chore again on Sunday. And the POP equals 25%. This is a chance of rain ruining the sealant job Saturday night. So, going through the math, in our case, the cost to loss ratio equals 1.5 hours divided by 7 hours, which equals 0.21. So the final figuring to see if weather planning should be taken, the 25 from the POP is greater than the CLR times 100, which is 21. So we can see that if POP is greater than the CLR times 100, then planning should be made to account for potential bad weather. So, in our case, planning should probably be made to account for potential bad weather. And in that case, we should just hold off on doing it Saturday and wait until Sunday to do our driveway sealing.